Hi everyone, my name's Ari and I'll be one of your GSIs for Chem 3B this summer. I thought it could be helpful to review some of the things you might have learned in Chem 3A or an equivalent organic chemistry course. Starting off, we use a lot of different arrows in organic chemistry. So let's clarify. I have 6 of the most common arrows here and their corresponding labels on the right. Without further ado, let's get started and match some of the arrows with their labels. Let's start with the single electron or radical arrow. This arrow is used to notate the moving of a single electron. It's not super common in Chem 3B, but it's important to be able to recognize that it's an arrow with a single barb. Below it, we have the reaction arrow. The reaction arrow is used to indicate the proceeding of a reaction from reactants to intermediates or products. Across from it, we have the corresponding no reaction arrow. This is a reaction arrow with an X through it to indicate that a reaction does not proceed. Above that, we have the equilibrium arrow. The equilibrium arrow is used to indicate the favorability of a reaction. An arrow that is larger in one direction than the other indicates that the reaction is more favorable in that direction. We also have the most common arrow you'll use in Chem 3B, the electron pushing arrow. An electron pushing arrow shows the movement of 2 electrons and typically corresponds with the formation or breaking of a bond. Finally, we have the resonance arrow. The resonance arrow is used to indicate the redrawing of a molecule to show a different arrangement of electrons across that molecule. Now, let's talk about some of the reactions that are fundamental to organic chemistry. At the center of organic chemistry, we have the acid-base reaction, in which a base is protonated by an acid. That is to say, a base gains a hydrogen from an acid. The curved arrows for this reaction are as follows. 2 electrons from the base form a bond with the hydrogen. The 2 electrons shared in the bond between the hydrogen and the acid are gained by the acid. The products of this reaction are a conjugate acid and a conjugate base. This is vocabulary you might hear in a lecture, so it's important to be familiar with a base, acid, and the corresponding conjugate acid and conjugate base. Next, we'll get into the nucleophilic attack. In a nucleophilic attack, 2 electrons from a nucleophile attack an electrophile, often resulting in the formation of a bond between them. In this case, we have a generic nucleophile attacking an electrophile. Now let's talk about some of the nucleophiles you might see in Chem 3B and might already be familiar with from Chem 3A. Starting with our super strong nucleophiles, we have the Grignard reagent, which is a carbon connected to magnesium and bromine. It's similar to a carbanion, which is a negative charge on a carbon. However, to indicate that it is not just a carbanion, but specifically a Grignard reagent, we include the bond to magnesium bromide. In practice, to draw a nucleophilic attack from a Grignard reagent, we show a curved arrow starting from the bond between the carbon and the magnesium bromine to the electrophile. Pardon me. Moving on, we have lithium aluminum hydride, which is a hydride nucleophile that is commonly used to reduce certain electrophiles. We also have nitrogens with a negative charge. Something to keep in mind is that as a molecule becomes more basic, that is, if we increase the basicity of a molecule, it often corresponds to an increase in nucleophilicity. Pardon me. Keeping that in mind, we have some other good nucleophiles. They're not as strong as the ones I just listed, but they are typically considered good nucleophiles. Please keep in mind that this isn't an exhaustive list, but just to get you thinking about what some good nucleophiles might be if you see them come up in a reaction. We have hydroxide, which is an OH with a negative charge, as well as alkoxide, which is a carbon bonded to a negatively charged oxygen. We then have amines, which are a nitrogen with 3 bonds. The most simple amine is a nitrogen bonded to 3 hydrogens, but it could be 3 carbons or other molecules as well, including combinations of hydrogens and carbons. Another sample of a good nucleophile is a nitrile group, which is a carbon bonded to a nitrogen with 3 bonds. Again, please keep in mind this is not an exhaustive list, but just some examples to get you thinking about what some good nucleophiles might look like. I'm also excited to learn some new ones with you as we work through Chem 3B. The next important reaction step to talk about is the leaving group leaves step. The curved arrow for this shows that the leaving group gains the 2 electrons in the bond between it and the molecule it is leaving. It results in the fragmentation of a single molecule into 2 molecules, 1, 2. Because the leaving group picks up the 2 electrons, it typically has a negative charge unless it was already positively charged, in which case it would be demoted to a neutral charge. Next, let's go through some standard reaction vocabulary you might hear in Chem 3B. Some of these words mean the same thing. For instance, reactive, high energy, and unstable are all words to convey the fact that a molecule is ready to react. Similarly, unreactive, low energy, and stable are often used interchangeably to discuss a molecule that is unlikely to react with another molecule. Now I'll briefly go over some mechanisms we learned from Chem 3A. First, we have the SN2 mechanism, in which a nucleophile attacks an electrophile and a leaving group leaves. In this case, the nucleophile replaces the leaving group to form a product in which the nucleophile is in the space the leaving group was before. Some notes for the SN2 reaction is that it requires a good leaving group, a good nucleophile, and low steric hindrance. If we started with a stereocenter as our electrophilic carbon, something to keep in mind is that if the first priority substituent is replaced by the nucleophile, the configuration would flip. For example, if this were a stereocenter with an R configuration, and then we performed an SN2 reaction at that carbon, the resulting molecule would have S stereochemistry. I know stereochemistry can be complicated to understand at first, so please come to office hours if you have any questions. Next, we have the SN1 reaction mechanism, in which a leaving group leaves, and then a nucleophile attacks. Like the SN2 mechanism, this results in the replacement of a leaving group with a nucleophile. As you can see, the leaving group has been replaced by the nucleophile in the product. Something to keep in mind about the SN1 reaction is that the rate and favorability of this reaction are determined by the stability of the carbocation intermediate. That's another good vocabulary word to know. A carbocation is a carbon with an unfilled octet resulting in a positive charge. You can remember it because we have a smiley face right here, so we smile whenever we see carbocations. To me, this sort of looks like a smiley face. Moving on to another reaction we may have learned in Chem 3A or an equivalent course, we have the E1 reaction. Like SN1, this is a reaction in which a leaving group leaves, creating a carbocation. However, instead of a nucleophile attacking, we have a base deprotonating to create a double bond in our product. Some things to keep in mind with the E1 mechanism is because it is so similar to SN1, and they often occur under similar conditions, it can sometimes compete with SN1. For instance, we could have a base act as a nucleophile in this case and attack that tertiary carbocation. Additionally, the rate and favorability of the E1 reaction, like the SN1 reaction, is determined by the stability of the carbocation intermediate. The last reaction we'll talk about is the E2 reaction, or the concerted elimination reaction. The curved arrows for this are as follows. A base deprotonates a hydrogen. The electrons from that hydrogen-carbon bond become a double bond. Then the leaving group leaves. I said then, but in reality, this reaction happens all at once. It's concerted. However, it requires very specific reaction conditions. It needs a good leaving group, a good nucleophile, or in this case, a base, and it also requires very specific stereochemistry. That is, the leaving group, which I'll circle in green, has to be opposite or anti to the acidic hydrogen. That is, they have to be on opposite sides of the carbon-carbon bond and have opposite stereochemistry. That's it for this review of Chem 3A, or your first semester of organic chemistry. I'm super excited to have you for Chem 3B, and if you have any questions, please don't hesitate to post them on Ed or come to office hours. Thanks so much for watching.